Hello, everybody. I'm Vishwas Narendra. I'm a senior software engineer on S3, and I was the lead engineer on S3's strong consistency delivery last year. With me are Sardar Tasiran, who's a principal applied scientist, and Ankush Desai, who's a senior applied scientist at S3. Today, we're going to be talking about how we delivered strong consistency and maintained correctness at S3 scale. As you probably know, S3 announced strong read after write consistency during reInvent last year. What this means is that if you have applications that are performing consecutive writes on to S3, a read that follows the writes will always return the last successful write. And this is a change from the eventually consistent model that S3 had in operation all the way from when it was launched in 2006 until late last year. What we announced in December was that all operations on S3 would be strongly consistent, and there would be no change in price or performance. This is obviously a huge benefit for data lakes because data lake users had to go through a few different workarounds for dealing with eventual consistency, but other users benefit from this as well. It's in the form of having a simpler programming model. Let's briefly talk about what we heard from our customers. We heard customers say this is huge and that this is a remarkable feat of engineering. In recognition of the fact that, a number of our customers recognize that this is a complex problem to solve, and we appreciate that. Many customers were appreciative of the fact that they could finally stop coding around eventual consistency now. What this means is that they didn't have to build workarounds, such as in data lake. In the case of data lakes, for instance, having to essentially have artificial weights between dependent jobs or using a secondary store, such as DynamoDB. We also heard some skeptical voices. We asked, customers were asking us, are there any exceptions? Can I really get rid of my workarounds? And we understand why customers ask us this. Strong consistency is a difficult thing to deliver at S3 scale. And we understand our customer skepticism in this. But here we'll go over what makes this hard briefly. It's the scale of S3, and there are a few dimensions to the scale. One, of course, is that we have exabytes and exabytes of data on S3. We have over 100 trillion objects. S3 handles tens of millions of requests every second. And internally, S3 is comprised of over 320 individual microservices. And these are all different dimensions that make solving a problem such as strong consistency hard, where we are changing the default behavior of pretty much every request that is being sent to S3. And so we realized that when we talk about something like strong consistency, we want to have absolute confidence in our solution. And this goes back to us recognizing why customers were kind of skeptical about this. And we thought of how we would build this confidence. And the conventional way we would build confidence in a software project such as this would be through the use of things like unit tests, integration tests, failure injection and stress testing, standardized test suites where we have test suites that are well known outside of Amazon and S3 and use them, adopt them to work internally. And then through the use of test workloads and canaries. And all of these techniques are great, and all of these are almost necessary, and we kind of think of these as the minimum bar for what we need to do to build confidence. But we recognize that for something like strong consistency, as I mentioned earlier, correctness is crucial. And consistency, we are trying to deliver strong consistency in a way to simplify the programming model. And so there is no such thing as 99% consistency, and we really wanted to make sure that we are truly 100% consistent. And the challenge there is that there's an astronomical number of possible behaviors of systems when we have this many microservices and this many possibilities of concurrency and failure, etc. And conventional methods, such as the ones that I spoke about on the previous slide, give you limited coverage, and they rely on human diligence. They might exercise the same code paths over and over, and there is no systematic way in which we explore all possible behaviors. We wanted to make sure that we go the extra mile to ensure correctness, so that you as the customer can use S3 strong consistency with confidence. To tell you more about how we used automated reasoning in this quest is Sardar Tasiran.
Thank you, Vishwas. I'm going to tell you about how we use a class of techniques called automated reasoning, also known as formal methods, to increase confidence in the correctness of S3 consistency. Like Vishwas said, with tens of millions of requests per second and hundreds of interacting microservices, system the size and complexity of S3 has an astronomical number of possible executions. And for each of these executions, we would like to raise confidence that it is strongly consistent. The tool we make use of for this purpose, we call automated reasoning, is the area that I and my team work on. And here, the key idea is to reason about all possible executions. And this is done using either mathematical logic proofs, which are carried out with computer aids, or by using clever algorithms to do systematic exploration of system states and ensuring that in each one of them consistency is preserved. At AWS, we have been making increasing use of automated reasoning for purposes ranging from security to functional correctness, and in areas ranging from the boot code at our data centers to our cryptography to our distributed systems, which is our topic here. I'm going to tell you in a bit more detail about how we use automated reasoning to raise the bar in S3 consistency correctness. When applying automated reasoning to S3 consistency, we took 3 views of S3 at 3 different levels of detail, 3 zoom levels, if you will. Each of these levels allowed us to focus on the different aspects of S3 consistency, and it allowed us to go after a different class of potential errors. At the top level, we have our most abstract model, the protocol level model. And here we have an overall view of the system and the logic underlying the S3 consistency design. Reasoning at this level is best suited for properties such as every key stored in microservice A is also in B. One level down, we have what we call our detailed design models, which refine the protocol level models. And here, we, in terms of state machines, implement desired properties such as event E1 always happens before event E2. And one more level down, we have, of course, the implementation code itself. And here our concern is, for instance, for a code expression, whether it computes the right intended logical condition for a state transition. Getting S3 consistency right, getting confidence, requires properties at each of these levels to be reasoned about, which is what we did. Roughly speaking, as you go from top to bottom in this diagram, in abstraction levels, you get more and more detail. You have full detail in the implementation code, of course. But as a result of more detail, the number of possible states explodes, and automated reasoning becomes more expensive. As a result, at higher levels, you're able to get a higher percentage coverage of possible behaviors modeled at that level. At the top level, protocol level model, we're able to give full proof. By deploying the right automated reasoning method and level for each kind of property we needed to establish, we were able to achieve overall confidence in S3's consistency. Now, let me tell you a bit more about our work at the protocol design and code levels. A protocol level model looks something like this. It's written in logic, and it is declarative, not imperative, not operational. And it describes the states and transitions, constraints on them that our S3 consistency design can take. The purpose of doing modeling and reasoning at this level is to establish system-wide invariance that we require for S3 strong consistency. Now, working at this level, we formally modeled all the protocols involved in S3 consistency. We then used what we call deductive proof methods, and we devised mechanized proofs of S3 consistency at this design level. What this amounts to is intuitively 100% coverage of S3 executions when viewed at this level. And proofs at this level are valid for any number of calls, keys, objects, servers. They're completely general. We're able to have full confidence at this level. The detailed design model refines the protocol level model and is expressed in terms of state machines that realize the protocol logic. State machine description here looks something like this. And the automated reasoning technique we use at this level, we call model checking. You'll hear more about this in more detail when Ankush takes over. The key idea here is systematically and algorithmically exploring different states and executions our system could get into at this level of detail. We're able to explore billions of edge cases routinely. Humans are notoriously bad at considering cases where a number of rare events all occur at the same time and how the design behaves in these cases. And this is where model checking excels. It's a really powerful method. It walks us through each of these edge cases and is able to give us confidence that we get consistency right in each of them. Ankush is going to tell you more about model checking. And I'm sorry, I misled you. After 2 levels of modeling, we have, of course, the implementation code itself, the thing that actually runs. And we would like to avoid coding errors in coding our designs, errors such as states being missing or state transition being implemented erroneously. This we call the code conformance problem. And what we do is establish correspondence between the implementation and the design model, doing something we call the code conformance check. We use the design model itself as a reference model, as an executable reference model, and we run it alongside the implementation code. As we explore the implementation code state space, as we execute it, for each step it takes, we look at the corresponding state at the design model level and check that it is consistent with what we designed. In this way, we're able to get confidence about the code executions, that they adhere to our design models and therefore are strongly consistent. So overall, we hardened consistency by working on these 3 levels, by using the appropriate trade-off, the appropriate automated reasoning for each property we were interested in. We got the most leverage at this middle blue layer, the design model level. And Ankush is now going to dive deeper into what we did here.
All right. Thanks a lot, Sardar. So like Vishwas mentioned, reasoning about correctness at S3 scale is challenging. It is challenging because it requires programmers to reason about all possible interleavings of messages and failures that can happen in the system. And as Sardar mentioned, we leveraged a technique called automated reasoning to allow developers to reason about the correctness of S3's consistency design and implementation. And one of the techniques that we used for this was model checking. So what do we need for doing model checking? What we need is two main things. The first being, we need a way in which we could write detailed formal design of our system. And for each component that is involved in the S3's consistency design, and also capture how all these components interact with other components in the system. What assumptions do they make? What guarantees do they provide? And so on. And after that, what we need is a way in which we can write correctness specifications for each of the component in the system, which then together give us the S3's consistency or strong consistency guarantee. So for doing this thing, what we did was we used a formal modeling language called P. P is a state machine-based programming language, which allows programmers to create formal models and specifications of complex distributed systems. P is a completely open source programming framework and toolchain. It is something that I built as a part of my grad school. And now we at Amazon, AWS, are the main contributors to this open source toolchain. What P actually allows you to do is it allows programmers to, it provides syntactic sugar so that the programmers can capture their high-level protocol logic as state machines, which is how normally programmers think about their system design. And what we did was we used P for creating formal models of all the core services which are required to be correct for guaranteeing S3's strong consistency design. And so we implemented the formal models, their detailed models, their interactions with all the components and the specifications as state machines. And after that, we used the backend model checker to analyze all possible states of the system and check whether the system satisfies the desired specifications for all those states. So to understand model checking a bit better, you can think of model checking as a search problem. Basically, it tries to perform a search over the whole state space of your design. So let's say, for example, your system is in a particular state where there are multiple concurrent actions that can happen simultaneously. And what the model checker really does is it explores all possible interleavings of these concurrent actions, which could be message interleavings, it could be different failures happening in your system or thread interleavings. So since the model checker performs systematic exploration of your state space, what it provides a benefit that it has this benefit that the probability of the model checker hitting a very rare combination of events is way higher than what if you were doing conventional testing methods. The other benefit is that model checkers basically use various approaches from automated reasoning to efficiently perform search of your state space. So one of the drawbacks of conventional testing methods like stress testing or random testing is that you end up doing a lot of redundant work, re-exploring the same behaviors and again, and hence wasting effort. Instead, model checkers use efficient techniques to explore your stir space with doing minimum amount of redundant work. So that's the real advantage, which allows developers to gain confidence in their design by doing exploration using model checkers. So apart from this efficient search as being a benefit for model checker, the other benefit is that if the model checker finds an error in your design, then it generates a deterministic error trace, which can be used to perform root cause analysis about what exactly went wrong and why the system didn't satisfy the desired specification. And if the model checker fails to provide any bugs in your system, what it really means is that if for all the states that were explored by the model checker, your system did satisfy the desired specification. So we did this kind of an approach for all the core services involved for providing S3's strong consistency. And the other thing was that we wanted to make sure that this was not a one-time thing. This is not something that we want to do only one time at the design phase. We wanted to make sure that this becomes part of the development process, and any change that happens in S3's consistency design is model checked and automated reasoning is performed on those changes. So we integrated model checking into the CI/CD pipeline, into our build and release pipelines to gain confidence and have continued assurance for our system. And for doing this, we leveraged AWS compute power. What happens right now is using AWS compute, we are able to explore billions of states in the design state space almost every day. and which then helps us to explore scenarios which require rare events to occur. Like very low probability cases that happen in production can be explored much more efficiently by running model checker on AWS compute. So to summarize, we found that model checking has benefits in all the phases of development lifecycle. When you are in the design phase, when you're creating formal models, model checking and automated reasoning acts as thinking tool. It forces the developers to think about their system rigorously, create reference specifications, and which in turn helps bridge the gap in their understanding. And like I mentioned, since model checking allows systematic exploration, it then helps developers uncover non-trivial bugs in their system and in turn gain confidence in their design. And finally, once you have done model checking, and since you have put model checking and automated reasoning in your pipelines, it provides continued assurance, which in turn leads to boosting the overall velocity of the developer, because now they can perform rapid changes in their design, perform iterations, and eliminate bugs early on in their development cycle. So overall, we found that this approach basically gives us enough confidence to deliver strong consistency to our customers with high assurance. And to conclude, I'll hand over to Sardar again.
Thank you, Ankush. So our message to you is that we went to great lengths to get S3 consistency right, to give you confidence in its correctness. Our approach was far from ad hoc. We were very systematic. In addition to putting a huge amount of resources into conventional testing, we went above and beyond, and we made extensive use of automated reasoning. We used a lot of state-of-the-art methods, mathematical logic, algorithmic techniques to get S3 consistency right. And we hope you'll enjoy it and use it with confidence. Thank you. Questions?
Awesome. That was a great presentation. I always geek out when I get to hear some of these, an explanation under the hood of how some of these developer level features like strong consistency work, and then get to see the underpinnings of it here. So my mind has been blown, and I know a lot of folks in chat are thinking the same. So I've got one question in chat here from Narakanan. Can model checking be used in general for all software development? And I'll let anyone who wants to jump in on that one take it. I guess maybe this is just more...
Sorry, I thought Ankush would jump in already.
Okay, yeah.
Ankush, go ahead, please.
No, sorry, yeah. So yes, you can use model checking in general at all levels of software development during design phase. Once you have created design, you can refine and create detailed design and perform model checking there as well. In fact, you can also perform model checking at the code level, where you systematically explore all possible behaviors of your concurrent non-deterministic code. So that you can actually in general use model checking. Yes.
To add to what Ankush said, both the model checking tools and the logic proof tools we used, we ourselves build and we open source them. So you too can use them on your designs and on your code. And we would be happy to support you in this effort.
Awesome, and I'd love to get that link to throw that in chat for everyone who's interested. I think really just this mind shift of working from first principles to create these checks using formal logic around what you intend to do before you even think about how you're going to author that in code or as a distributed system is so fascinating. Is there anywhere in particular folks can find that tool? You said it's open source. I can go hunt down the GitHub link and share that.
I am going to share it in a second.
Perfect. Thank you.
It's not letting me.
Well, Sardar, while you're looking for that,
here's the address here on my slide. If you don't mind sharing it.
There we go. So P and the P org there. If folks are at all interested in more of these under the hood talks, is there anywhere you could point them to? Maybe past reInvents, summits, and any other place where folks can see some of the work that your team's doing?
Our consistency work is rather new. We're going to publish scientific articles like the ones you saw. And we're going to also write blog entries. At that point, we'll be happy to point our customers to the automated reasoning work. About consistency in general, Vishwas, where would you point our customers?
Oh, Vishwas, I think you're on mute.
There's an entry on the AWS blog about the announcement itself. There's also related news on the Amazon open source blog. I forget what it's called, but that has a link to some of the open source contributions we did. So that gives you a little bit more detail about some of the things that we had to do as part of delivering strong consistency. There's also, of course, the AWS service documentation itself, which talks about how to use it and what you can expect.
Awesome. So it really sounds like a concerted effort here. We've got the docs, we have the developer-facing feature announcements on the news blog. I'm imagining the white papers will be announced at some point over on the Amazon Science blog. So wherever you typically consume content, I'd imagine you'll start to see some things here from all of you and your team. Awesome. Well, hey, I wish we could ask even more questions. Lots of exciting chatter from Twitch chat here, but we have a jam-packed schedule. Want to say thank you, Serdar, Ankush, and Vishwas for this talk. 3 presenters flew through this in 30 minutes, but it was super informative.